So is my screen visible to all of you? Is my screen visible?
Yes, ma'am.
Okay. Okay, so guys, good evening to all of you. Today we are going to discuss about this course Introductory Organic Chemistry Part 2, which is a NPTEL platform course, and the course instructors are Harinath Chakrapani and Professor Neeraja Dashaputri from ICER Pune, and I am Simran, your PMRF teaching assistant. So this is the third lecture which is taken by me. So I hope the two lectures which I have taken previously is clear to all of you. If you guys have any doubt regarding the previous lectures, please let me know in the starting so that we can take up the third session. Any questions, any queries regarding the previous lecture which I have taken? Okay, so if there is no question, then I'm moving forward with this third lecture.
No, ma'am.
Okay. Okay. So week 3 is about addition reactions or on carbonyl group. So today we are going to discuss about some reactions of carbonyl compounds. So previously we have discussed about the NMR, IR, and obviously the nucleophilic aromatic and electrophilic aromatic substitution reactions. So today we are going to discuss about these addition reactions. So coming to problem number one. So guys, in problem number one, just a second. Okay. Yeah. So in problem number one, the question is asking which of the following predominantly gives the conjugate addition product with pent-3-ene 2-on. So you have to answer that which of these options, which of these nucleophiles will give you the conjugate addition with this pent 3e 2-on, that is this compound, this alpha beta unsaturated carbonyl compound. So which of these among these four will give you the conjugate addition? What is meant by the conjugate addition? 1,4 addition. So guys, first of all you need to know that these alpha beta unsaturated ketones will undergo the nucleophilic reactions in two manner. One is 1,2 in 1,2 fashion and in 1,4 fashion. So what is meant by this 1,2 and 1,4? So if the nucleophile is adding on this position, this is 1, 2, 3, and this is 4, right? So if the nucleophile is adding from this carbon, then you will say that it is 1,2 addition. And if the nucleophile is adding on this carbon, and then this bond will migrate here, and then this will migrate here to give you a alpha beta unsaturation at this 2 3 position, right? So if the nucleophile is adding from this position, that is the beta position of this carbonyl carbon, then you will say that yes, 1,4 addition is taking place. So conjugate addition is the 1,4 addition, not the 1,2 addition. It is the 1,4 addition. So conjugate addition is which of these nucleophile from 1 to 4 will give you the 1,4 addition. That is meant by conjugate addition, right? So now you have to answer based upon the HSAB theory. What is this HSAB theory? Hard and soft acid base theory. So, can anyone tell me among these four which one can give you the conjugate addition product with this alpha beta unsaturated ketone? Any guesses? I have already
Sea water, copper.
copper. Okay. So how this copper is giving the conjugate addition? Just take a look on that. See, I have told you that 1,2 addition is the direct addition and 1,4 addition is the conjugate addition. That is the alpha. That is the addition of nucleophile at the beta carbon of the alpha beta unsaturated compound. So now here comes the role of HSAB theory. So first of all, you need to know that this alpha beta unsaturated ketone or aldehyde or the carbonyl compound has two electrophilic centers, right? One electrophilic center is this, and second electrophilic center is this. Because now there is a conjugation which is happening in the alpha beta unsaturated compound. That is why this center now becomes the less electron rich center, right? And this second center will become, because a partial double bond character will arise here after the delocalization. So this center is now the electron dense center. It is an electrophilic center, but now it is a hard center having the high electron density compared to 4. So if we go by the numbering, then the carbon 2 is having higher electron density than carbon number 4. So that is why they have given a theory that this is a soft this is a soft nucleophile attack position, and this position belongs to the hard nucleophile. So this is a soft electrophilic center, and this is a hard electrophilic center. So now this carbon number 4 is a soft electrophilic center, and carbon number 2 is a hard electrophilic center. So according to soft acid base theory, hard center will attack hard acid, or hard base will attack on the hard electrophilic position, and the soft nucleophile will add on the less hard, that is the soft electrophilic center, right? So basically soft will add to soft and hard will add to hard. So what is this? So here they have described the classification of acid and bases on the basis of hard and soft rule. So here this lithium, sodium, potassium and magnesium. So coming back to question, you have different metal, right? All of these are nucleophilic additions, but there is a catch, that is the metals are different. So here magnesium is there, lithium is there, here copper and lithium are there, and this is magnesium again. So we are talking about four metals, that is magnesium, lithium, copper and magnesium again. Three metals. So now you can see from this table that magnesium, lithium and what? This basically they belongs to hard family, and copper belongs to soft. So that is why now if you compare it with that particular knowledge that the lithium and magnesium are hard hard metals, that is why they will attack to the hard electrophilic center. That means they will give you 1 2 addition product, not the 1 4 addition product, right? But if you compare about the copper, we have seen that it is a soft metal. So if it is a soft metal, then it will attack to this 4, that is the soft electrophilic center. So now it will give you a attack at the beta position of this alpha beta unsaturated carbonyl compound. So copper is the only metal which will give you the alpha beta unsaturated conjugate addition, right? So it in between these four, this magnesium, lithium are the hard metals, whereas the copper is soft metal. That is why it is given a conjugate addition. So if we take some examples, here also you can see that nitrile is giving you the 1 4 addition on this alpha beta unsaturated compound. This this alkoxide is also giving you this particular reaction, and this Gilman reagent, that is the copper based reagent, it is also known as the Gilman reagent, it will give you the conjugate addition. Coming back to the question now, the conjugate addition will be given by the metal which will attack at the soft electrophilic center of the alpha beta unsaturated compound, and that should be a soft metal. So here copper is the soft metal, so it will attack on the beta position. So here it will give you the conjugate addition. So option number C is the right answer. Is it clear to everyone why copper is giving the conjugate addition and not the magnesium and lithium? Is it clear? If it is clear, then I am moving forward. Clear to everyone?
Yes, yes, ma'am.
Okay. So if it is clear, then coming to question number 2. So in question number 2, they are asking which is the main final product of the following reaction. So this is the reaction and you have to find out the product. So what will happen when this first and second condition will react with your starting materials? So here you will have a sodium ethoxide and ethanol. So what is a sodium ethoxide? Acid or base? Base. So what will base do? It will abstract a acidic proton. See, sodium ethoxide is a very strong base. So it will abstract a acidic proton. So where is the acidic proton present in the system? So this is the methyl protons, right? This is the methylene protons. So where is the acidic proton that is present in the starting material? Can anyone tell me?
CH2.
Yeah, the methylene protons are the acidic proton. Why? Because here after the generation, see what is meant by the acidic proton? Acidic protons are those where if the abstraction takes place, the carbon ion is highly stabilized. So here if the abstraction of this proton is taking place, then the carbon ion which is getting generated here is highly stabilized. Why? Because of the presence of these two carbonyl groups. Here the delocalization is there, and also similarly it can delocalize here as well, right? So that is why it becomes, these two hydrogen becomes very much acidic. Okay. So sodium ethoxide first of all will abstract a proton from this side, and carbon ion is getting generated. Then what happens? It will attack to either beta position or 1,2 addition. It can add to your alpha beta unsaturated carbonyl compound in two ways, either way, 1,2 addition or 1,4 addition. So, can you tell me, anyone know what will happen, 1,2 or 1,4? Which pathway it favors?
1,4.
1,4 addition. Why 1,4? Because, guys, you have to keep one thing in the mind. Aside from the HSAB theory, what will happen that if your nucleophile which is attacking is resonance stabilized, right, having the resonance like this, here your nucleophile which is getting generated at the carbon ion is resonance stabilized. So if there is a such stabilization which is there, then then the nucleophile become the soft nucleophile, right? If there is a stabilization of your nucleophile either by resonance, then it becomes the soft nucleophile. So now it will prefer to attack on the soft side of the alpha beta unsaturated carbonyl compound rather than the hard side. So if your nucleophile is gaining the stability from the resonance or some other factor, and it becoming stabilized, then you can say that yes, now it is becoming a soft nucleophile. So that is why it is attacking to the beta position rather than the 1,2 addition. You will have a Michael addition here, or you can say the conjugate addition here. Okay, so it will attack to beta position. So here, what will happen? First of all, this anion is getting generated, right? And then it will attack onto this position, that is the beta position. This will go here. This bond will migrate here. Okay, so now, because of the presence of ethanol, so this will come down, and again you will have a ketone at this site. So only this group is getting attached at this carbon, carbon number 3. Okay, so this carbon, carbon number 3 is taking up this particular group which is adding up here. So now this much is for first reaction, right? And the second, what they have added in the second step, they have added HCl water. Okay, so they have added HCl and water and then heated it. So now what will happen? See, you have this compound, they have added HCl, and you know that there is a ester which is present. Okay, there is a ester group which is present. So now in the presence of HCl, it will get hydrolyzed. So in the presence of acid, it will get hydrolyzed to give you acid. Because esterification is a reversible step, so now in the presence of ethanol and sodium ethoxide and acid, what will happen? This acid group will go into the acid. This ester group will go to acid. Hydrolysis will take place, and in the same pot they have heated the reaction. They have heated the reaction. So now in the presence of heat, there is a decarboxylation which is happening in the acidic medium. So decarboxylation will take place, and this CO2 will leaves out to give you this particular compound. So what happens? There is a mechanism between this CO2 liberation. So here you are arriving at this situation, right? So they are describing about this functional group only. So here you have similar kind of system, a ketone at the beta position, right? So here also what will happen, this ketone will take up the proton. In this case we have this proton of acid. Here also they have the proton of acid. So this ketone will take up the proton. Now this bond will migrate here, and this bond will migrate here to liberate the CO2 molecule. So after the liberation of carbon dioxide, what will happen? Enol tautomerize to ketone under the acidic condition. So here acidic condition is present in the medium, that is water is present and HCl is present. So after the liberation of CO2, this alcohol again isomerized to give you the ketone. So similarly, it is happening in our case. After gaining the OH proton here, it will again isomerize to give you this ketone. So this is how the two steps is taking place. So now what, tell me which is the correct option?
B.
B. Option number B is the correct option. So first of all, we have seen that in the first step they have added a strong base in ethanol, that is a solvent. So now base will abstract the proton which is very acidic, and now in our case this active methylene group is present and the hydrogens are highly acidic, so they will abstract a hydrogen here and a carbon ion gets generated. So after the generation of carbon ion, the trick was to think that either 1 2 addition will take place or 1 4 addition will take place. Once you figure out 1 2 or 1 4, then the life is easy. So you can now predict that yes, 1 4 addition will take place rather than 1 2, because of the soft nucleophile which is getting generated. So after the Michael addition, the product, the second step is the hydrolysis of the ester group and the decarboxylation to give you the product. So is it clear to all of you how this reaction is going on in both the steps? Is it clear, guys?
Yes, ma'am.
Okay. It is clear, then I'm moving to problem number 3. See, this is also a similar kind of question. So just quickly tell me what will happen. See, this is a base. Again, the same base, sodium methoxide. It is a strong base, it will abstract a proton. So which proton it will abstract? This proton or this proton? 1 or 2?
2.
2. Why 2? Because after the generation of carbon ion at this center and carbon ion at this center at 1, right? So this carbon ion is getting stabilization via only one carbonyl group, right? But if you can see here, this carbon ion is stabilized by both the carbonyl groups, right? So that is why we can say that this carbon anion that is generating is highly stabilized rather than one, the two is highly stabilized. Okay, so that is why we are saying that yes, this carbon ion is getting generated. Okay, the carbon ion is getting generated. After that, what will happen? 1 4 attack will take place or 1 2 attack will take place?
1 4.
1 4. Again there is a situation. See this nucleophile, now you have to figure it out, it is a soft nucleophile or hard nucleophile. So I have told you that the nucleophile, if it is stabilized by resonance, then it is a soft nucleophile. So here also this nucleophile is getting stabilization via two carbonyl groups. So that is why it is making it a soft nucleophile. So if it is a soft nucleophile, then it will add to the soft center of the alpha beta unsaturated compound, right? So now this will again go here and this will go here. So again, Now what will happen? This much you have arrived on, right? Now what will happen? That in the same pot you already have excess of base present. Then what will happen? Now tell me, this acidic proton is there, two acidic protons are there, right? Basically here and here. So 1 and 2. So base has to abstract a proton again, the acidic proton. So now which will be more acidic, 1 or 2?
2.
2. Why 2? Because if the carbon ion is getting generated at the position second, then what will happen? It is stabilized, and if it is generated at one position, then also it will get stabilization. But guys, here also the plus I effect of this methyl is also there, right? So here the electron density is higher than this ethyl group. There is a higher chain which is present, and that is why there is a more electron crowding here, and the negative charge will try to be at that position where the methyl groups are less. So here at second position it will get generated, right? So now if it is getting generated at position number 2, then what will happen? Okay, so I've got it that it is a negative charge. Then what? So here, after the generation of this negative charge, now there is a ketone which is present here. This is the electrophilic center, right? And if you can count that this is one carbon, two, three, four, five, and six, right? So if you can if you can see here that this carbon ion then attack on this carbonyl carbon of C6. After attacking of at this position, what will happen? A six-membered ring again. The fused six-membered ring gets generated. This alcohol is getting generated. See, yeah, here there is a own minus which is getting generated, right? After the addition of this nucleophile to the carbonyl carbon. So after the formation of this oxyanion, you have protic solvent in the system. So if you have protic solvent, then it will become OH, right? So at this position, you have this OH, this OH, and at this position you have hydrogen. Just forget about the alkene. So here you have OH and here you have hydrogen. So after the dehydration, this alkene is getting generated, because what is the driving force of the generation of this alkene? Now here after the dehydration you will get a alpha beta unsaturated ketone that is highly stabilized. So that is why a dehydration step is also taking place, and you will get a alkene generated at this position, right? So tell me which is the right answer, which is the correct option?
Third one. C.
Option C. Okay.
C.
Option number C. Right. So basically there is a Robinson annulation which is taking place. First of all, Michael addition and followed by aldol condensation, right? So this is a Robinson annulation. This is a name reaction which is taking place here to generate a fuse system. 6 is fuse system. Okay. So is it clear to all of you?
Okay, ma'am.
Okay. So if it is clear, then I'm moving to problem number 4. So now in problem number 4, you have to identify in which of the following equation is the outcome wrong. So now you have to figure it out which is the wrong reaction. So one by one we will be going through the reaction. So coming to part number 1. So they have treated this aniline with sodium nitrite, HCl water, and in the second part they have treated it with copper cyanide to get this nitrile group at this position of amine. So what which is the first reaction? Can anyone tell me what is this reaction?
Diazotization.
Diazotization. So what will happen? This aniline, this amine group will convert into N2, right? So diazotization will convert this into the N2 group. like this. Here a diazonium salt is getting generated. Fine. After that, copper cyanide will attack on that azide which is generated here, N2Cl, diazonium. So cyanide will attack on this diazonium salt and it will leave out, right? So this is how you will generate a cyanide group at the position of amine. So this reaction is right or wrong? What do you think?
Correct.
Correct. So coming to part number 2 now. So part number 2. A diazonium salt is already generated and they have treated it with water and heated it. So if water is the nucleophile here, then they have generated the benzene ring. So is it right or wrong?
Right.
Right. Okay. Then coming to part C. So here what will happen? The sulfur has the lone pair, right? And they have treated it with pyridine. Pyridine is a base. So pyridine is a base. So what will happen? What will base do? Base will abstract a acidic proton, and thiol proton is acidic enough to be abstracted by pyridine. So here a negative charge is getting generated. So here, as I have told you, the nucleophilic aromatic substitution reaction will take place. Cl will knock out, and you will get this SCH2PH at this position. So previously, in the previous lecture, we have discussed about the nucleophilic aromatic substitution reactions. So this is an example of that reaction only. So is it right or wrong? Anyone? Is this reaction a right or wrong reaction? Just think about the outcome of the reaction. Is it correct or not? Any answers? Any guesses only? Okay. So here I have told you previously in the previous lectures
Full
that
product is meta substituted.
product must be meta substituted.
Yes, ma'am.
Actually, you are thinking from the point of view of a sodium amide group, right? We have talked about the amide group, amide base, right? So you are thinking that a benzene is generated and then you are attacking the nucleophile, right? So it is not the case. Pyridine is not that much acidic enough to abstract the proton of the benzene ring. So it is a base, but not that much. Like it has a less basicity than sodamide. Sodamide is very much basic. Okay, so you need that base to abstract the proton from the benzene ring to generate the benzene. But here benzene is not going to generate. Here what will happen? This will simply make your thiol a better nucleophile, and it will this nucleophile will act here, as I have told you, in the nucleophilic aromatic substitution reaction, that first addition and then substitution will take place, right? Remember, so here first addition at this position and then elimination of this Cl will take place. So simply you will get the substituted product at the position of the leaving group only, not the benzene case. So is it clear why it is right?
Yes, ma'am. Yes, ma'am. Clear.
Yeah. So you have to also think about the basicity of the base. So if it is not that much basic, then it will not going to abstract that benzene proton. It will uh, only make your nucleophile activated, right? So coming to the option number D. So in option number D, here they have used the sodamide. See, now there is a possibility that it will abstract the proton from the ring. So which proton? Here is the possibility and here is the possibility, right? Two protons are there to generate the benzene. Benzene can be generated either way, here or here, right? Either way it can be generated. So they have given you three outcomes. So sodamide is getting attacked here, over here, and over here. So can anyone tell me that is the outcomes right or wrong? Is this reaction right or wrong? Think over it. In previous class we have discussed these two reactions C and D. So what do you think, that is it right or wrong? The part D.
Possible product or second and third products are possible.
Okay. So you think that out of three, two are possible, right? But just tell me that there are two hydrogens which can be abstracted by the sodamide. If it is abstracted by this way, then the benzene is going to generate here. If the benzene is going to generate at this position, then sodamide has two position to attack, one and two, right? If these are basically the possible products they are writing, they are not writing it that it is a major product, minor product, or intermediate, whatever. They are just saying that it could be the possible products. Here also the hydrogen is present, and it can generate the benzene at this 2 3 position also. So sodamide had two position to attack, two or three. So basically, they are telling you, they are trying to convey that this sodamide can attack at 1, 2, and 3. All the three possible positions can be attacked by the sodamide because benzene can be generated at 1, 2, and 2, 3 position because of the presence of hydrogens at that position. So that is why they are not giving you that it is a major product, minor product, but they are just telling you that yes, these three can be the possible outcomes, right? So now just understand that, and now tell me, is it right or wrong? Anyone? So let me tell you that yes, it is the right thing because they are just telling you the possible outcomes, and I've told you that yes, these two hydrogens are present, and benzene can be generated at both the position 1, 2, and 2, 3. That is why they are telling you the possible outcomes that sodamide can add on 1, 2, and carbon number 3. So three possible outcomes are there. So D is right, C is right, A is right, but coming back to B. Guys, you have told me that yes, this is a right statement. Here, these two reactions are interlinked. They have added in the first step the diazotization. So they have given you directly the diazonium salt. So here they have make the diazonium salt, and then they have attacked this nucleophile copper cyanide. So cyanide will attack to the diazonium salt, and diazonium salt will leave out. Right? This CN will attack on this carbon, and this diazonium will leave out. Right? So similarly, guys, here also nucleophile is water. What you meant by water? This oxygen lone pair will attack again to this, and this will leave out, right? So if it is attacking on this position, then this OH group will add on this carbon, na? Rather than hydrogen, there should be a oxygen hydrogen that is present in that nucleophile case. Is it right or not? Because here you can say clearly see that cyanide is attaching at this carbon where the diazonium salt is getting formed, and after that the nucleophilic addition is taking place. But in the second,
OH.
yeah, what OH? Yeah, what I'm saying is this outcome is wrong. Why? Because The nucleophile is water, and that means that here you will add a OH group at this position rather than the hydrogen which is shown in this case. So that is why we can say yes, the B statement, the B outcome is wrong. So is this much clear to all of you why the B is wrong? Is it clear, guys, why B is wrong? Why you are getting a OH group at this position of diazonium salt rather than hydrogen?
Yes, ma'am.
Okay. So then, if it is clear to all of, I hope all of you are understanding these concepts, not the single person who is answering. So I just hope that all of you are getting this. So if you are not getting this, please ask me again. I am here only. I will tell you again what is the reason behind it or what is the question. So just tell me what is not understandable for you guys. Okay. Okay. Now, so I think all of you have got this problem number 4. So coming to problem number 5. So here they are asking which aldehyde has the smallest equilibrium constant for the formation of a cyanohydrin. So they are asking you which aldehyde has the smallest equilibrium constant. What do you mean by equilibrium constant? The facile, how much facile the reaction is towards the formation of cyanohydrin. Basically, equilibrium constant is the how much the forward reaction is going on. Okay. So for that, you need to know what is the cyanohydrin. So the mechanism of cyanohydrin formation follows this pathway. So just connect with this pathway, then connect with this mechanism, and then you will get to know which aldehyde will has the smallest equilibrium constant for this particular reaction to goes on. Okay. So what will happen in cyanohydrin reaction? So cyanohydrin is where a cyanide group will attack on this carbonyl carbon to give you this alkoxide, and this alkoxide then takes a proton from this HCl to give you OH. So carbon having the cyano group and the OH group is known as the cyanohydrin, containing both the cyano and oxygen, that is the hydroxy group. So here it will come the term as cyanohydrin. So mechanism of cyanohydrin formation follows first of all the nucleophilic attack and then the deprotonation. So here first of all the cyanide will attack on this carbonyl carbon, and then this alkoxide anion will take up the proton to give you a cyanohydrin complex. So coming back to the question, so just see this process first of all, that yes, a nucleophilic attack is taking place and then the alkoxide will trap the proton. This will give you the cyanohydrin. This much is the mechanism for cyanohydrin formation. Okay. So now coming back to the question. Now they are asking you the smallest equilibrium constant. So which will be having the smallest equilibrium constant? The aldehyde, which is less facile to give you the formation of cyanohydrin, will has the smallest equilibrium constant, right? So coming to all the options, so first of all, in option number A, if the cyanohydrin will form, then what will happen? This cyano and this OH is getting formed, right? This will become a single bond. So here, first of all, the attack is taking place by the nucleophile, right? That is the cyanide. So nucleophile has to attack on this carbonyl carbon. So now tell me, in which carbonyl carbon the nucleophilic attack is facile? Among these four, which is the carbonyl carbon in which the nucleophilic attack is very much facile?
Option D.
Option D. Okay. So guys, facile means that which will attack the nucleophile readily. So here, nucleophile will attack on that carbonyl carbon which is electrophilic, right? So higher the electrophilicity, higher is the probability of the nucleophile to get the to get to attach to the particular carbonyl carbon, right? So here, when you come to all of these parts, you can clearly see that here there is a methyl group which is connected, here the methoxy group is connected, and here is the chlorine group is connected. So which is the electron withdrawing group and which is the electron releasing group? Here methyl is connected, which is somewhat electron releasing. So here it will give the electron density to this particular ring. If it is conveying the electron density, what will happen? This carbonyl carbon is now not that much electrophilic, which is there in this particular case A. If there is no substituent, this is electrophilic, right? Carbonyl carbon in turn is electrophilic, but if you are attaching the substituent at the aromatic ring, then the nucleophilicity and the electrophilicity of that particular compound varies. So how it is going to vary? That A, if you take as a standard, then in B, the electron density at this carbonyl carbon is high. Why? Because methyl group is attached at the aromatic ring. Now coming to part number C, here the methoxy group is attached. What is mean by methoxy group? It is the high electron releasing group. So here the lone pairs of this oxygen will take part in the conjugation, right? If it is taking in part in the conjugation, then what will happen? It will increase the electron density at this carbon. But now coming to part number D, Cl. It is the electron withdrawing group. See, chlorine having the electron negative atom, it will withdraw the electrons from the aromatic ring and make this center electron deficient. So in all the cases, we have seen that in methyl and methoxy is having the highest electron density at this carbonyl carbon. Then methyl is going to have the electron density at the carbonyl carbon. Then the part A will have the electron density. At last, you will have the least density will be present at the carbonyl carbon, which is having the Cl group, which is attached at the aromatic group. Why? Because Cl is an electron withdrawing group because of the minus effect. Now it will abstract the proton from the aromatic ring, and carbonyl carbon becomes the electron deficient carbon, right? So in all the cases, we have seen the least electron rich carbon is option number D. Here you will have a least electron electron rich carbon, right? So here higher electrophilic carbon is there. So higher the electrophilicity, I have told you, higher will be the higher will be the rate of the nucleophile to get attack on this carbonyl carbon. So this is also, they are what they are asking you, which aldehyde has the smallest equilibrium constant. So now the nucleophile will add to this part D at higher rate, right? Now they are asking the opposite. They are asking the smallest equilibrium constant. Smallest means the nucleophile will attack on that carbonyl carbon very less. So now which is the correct option for the smallest equilibrium constant? See, option number D has the highest equilibrium constant to attack the nucleophile. But which is having the smallest equilibrium constant? Can anyone tell me?
C. Option C.
Option C. Option C will be having the smallest equilibrium constant. Why? Because the electron density at this carbonyl carbon is very low. Sorry, very high. Because of the presence of methoxy group, which is electron releasing group. So because of the electron releasing group, now the electron density at this carbon is very high. So nucleophile will not go at this carbon very readily. So that is why option number C will be the correct option. It has the smallest equilibrium constant for the formation of cyanohydrin. So is it clear to all of you why the option number C is the correct option? Is it clear, guys?
Yes, ma'am.
Okay. So if it is clear, then coming to problem number 6. So, problem number 6, they are asking which ketone has the largest equilibrium constant for the hydration. So, which ketone has the largest equilibrium constant for hydration? So, you have to figure it out that now similarly, as we have seen the equilibrium constant problem in the problem number 5, so here you are asking, they are asking that highest equilibrium constant for hydration. So what will happen in hydration mechanism? So now you have to know about the hydration mechanism. So similar to that particular cyanohydrin formation, the hydration mechanism is also somewhat similar. What will happen? So here this OH minus that is coming from the water. Hydration is addition of water. So addition of water means your OH minus is getting attacked on this particular carbonyl carbon. So similarly, it will attack, first of all the nucleophilic attack will take place, and then the protonation will take place to give you the hydration. Okay. So here also what will happen? Your OH minus, which is a nucleophile, which is a nucleophile, right? So now this OH minus will attack on this carbonyl carbon to give you the hydrated product. So now what will happen? Your sp2 carbon is going to sp3. Your sp2 carbon is going to sp3, going to sp3, because double bond is now getting reduced to single bond in the hydration step. So similarly, you have to figure it out that the attack of nucleophile will take place in which case. So higher attack, like facile attack of nucleophile, will takes place in which of the case? A, B, C, or D? Can anyone tell me that nucleophile, that is OH minus here, will attack on this carbonyl carbon readily, or the B or C or D? Which carbonyl carbon is attacked readily by the nucleophile? Can anyone tell me?
A.
A. Okay. So here, any other answer than A?
B.
B. Okay. So guys, you have to first think about the electrophilicity, which we have seen in the problem number 5 as well. But now there is another concept which is coming in the rings. What is that concept? The strain concept. So we have seen that according to the Bayer strain theory, here this cyclobutanone is more strained than cyclopentanone, and cyclohexanone is also strained molecule. So here your sp2 carbon is getting into sp3 carbon. So strain is getting somewhat released because your sp2 carbon is getting to sp3. So that is why what will happen? This OH minus will attack on that particular carbonyl carbon at after that the formation of this product is highly stabilized. So you have to think about the product, and then you have to answer that product formation in which case will leads to higher stability for the product. So here if the nucleophile is going to attack on this carbonyl carbon of cyclobutanone, the ring strain is getting somewhat released because now the sp2 hybridized carbon is going to sp3. But if you say that yes, according to this strain theory, you will attack this OH minus to this position at the cyclopentanone. So just tell me, in between this A, B, and C, which is less strained, least strained means cyclobutanone, pentanone, hexanone, which is least strained?
C. C.
C. C or B?
Cyclopentanone.
Yeah,
Cyclopentanone.
cyclopentanone, because as we can recall, according to the Bayer strain theory, what will happen that the dihedral angle of this rings should be 109.5, but here it is going to 120, and this is the only angle which is somewhat closer to that particular dihedral angle given in the Bayer strain theory. That is why we can say that yes, cyclopentanone is less strained than cyclohexanone, and it becomes the least strained molecule, least strained. And the highly strained molecule is cyclobutanone. This A is highly strained molecule. So that is why we can say yes, it is readily available for releasing the molecular strain. So if one has to given the choice of A, B, and C, then which molecule will want to like release the strain quickly? A, B, or C? Which will be the molecule? which wants to release the strain very quickly?
C.
C or A? See, I am saying that if you have a choice, you are getting a chance to release the ring strain, then which particular molecule will grab that chance very readily? Is it the cyclobutanol, pentanol, or hexanol?
Pentanol. Cyclopentanol.
Cyclopentanol. No, see, here the concept is, see, this cyclobutanol is very much strained, right? We have talked about it. According to the Beer strain theory, cyclobutanol is highly strained molecule. So if it is getting a chance to liberate some of the strain, then it will grab that chance very quickly, because here your sp2 carbon is going to sp3 and somewhat strain is getting released. So here it will take that nucleophile very readily. So here the nucleophile will attack on that carbonyl carbon, after which there is a ring strain release for that particular compound. So here the nucleophile will add on the cyclobutanol very readily, then cyclohexanol, then cyclopentanol. So if we are comparing these three rings, then nucleophile will attack on first on the cyclobutanol, second on the cyclohexanol, and third on this cyclopentanol. So, is this much clear to all of you why this 1, 2, and 3 numbering I have given? Is it clear? Any queries, any doubt, please ask me. Is it clear, guys?
Yes, ma'am.
Okay. So, if it is clear, then we can say yes, the largest equilibrium constant for hydration will be of which option? Largest equilibrium constant means readily the nucleophile will add on that. So, we have seen that option number A having the facile attack of the nucleophile. So we can say yes, the largest equilibrium constant for hydration will be of option number A. So is it right? Is it understandable, the things? Any queries in this question? Okay, so if it is understood by all of you, if there is no query, then I'm moving to problem number 7. So problem number 7. So they are asking, predict the plausible products in the following hydride addition reaction to 2-butanol. So this is hydride addition reaction to this particular ketone. They have written wrongly. So here you have to answer that what are the possible product that could be formed via the LAH reduction and after that hydrolysis. So this is a very simple question. Can anyone just answer me what will happen if you just reduce this ketone with LAH and after that you hydrolyze it? So what could be the possible products? Any guesses?
See both.
See both. Okay. Any other answer? Okay.
But SN are protected.
Huh. So here what will happen? See, lithium aluminum hydride is a reducing agent. So it will reduce your ketone. So it will reduce the ketone aldehyde. So what will happen? This is the mechanism of the reduction. So this is the lithium aluminum hydride. So aluminum contains the Al minus charge. So then it will give a hydride basically. So here in our case we have this ketone. We can look at this mechanism. It is of aldehyde, it is of acid, so we can go through this mechanism. It is of aldehyde, but we have ketone, so similar mechanism will follow for the ketone as well. So it will give you a hydride at this carbonyl carbon, and then this oxygen will chelate with this aluminum to give you this tetrahedral intermediate. After that, the second step is the hydrolysis. So in the hydrolysis, this aluminum oxygen ball will cleave out and you will get the alcohol form. So here, if you have the alcohol as the product, then what will happen? Then both, then what will happen is hydride can add at both the surfaces. See, there are two faces of this particular carbonyl carbon. So either it can attack on the above face or either the hydride can attack from the lower face. So both the faces are available for hydride to attack. So there is a possibility of the hydride to get attacked by above the face or below the face. So here you will see a mixture of product because there is no selectivity which is mentioning in this question or the starting material. It is not at all selective. That is why you will end up having a racemic mixture. That is both S and R product will be the will be forming. So here there is no selectivity. So hydride will attack either from below or either from above face. So both faces are available, and that is why you will have a racemic mixture in the product. S and R both can form. So is it clear to all of you why both the compounds are getting formed in this reaction? Just look at the LH reduction step. First of all, the hydride from aluminium will transfer to this carbonyl carbon and this oxygen then chelate with this aluminium. And in the hydrolysis step, simply the aluminium and oxygen bond will cleave out to give you the alcohol. Right? So here the main step is the hydride addition. So hydride has two position to attack, either above the face of the carbonyl carbon or below the face of the carbonyl carbon. So it can attack on both the faces because there is no selectivity in the reagent, there is no selectivity in the starting material. So you will end up having a racemic mixture in the product. So you will have both S and R alcohol. So is it clear? Is it clear, guys?
Yes.
Okay. And moving to problem number 8. So among the following compounds, one that will not show keto-enol tautomerism. So you have to answer that among these compounds, which is the compound which will not show you the keto-enol tautomerism. So now you need to know the what is keto-enol tautomerism. So here what will happen? See, keto-enol tautomerism arises when you have the alpha proton present at the position. So here, if the carbonyl carbon have the alpha proton which is present, so this alpha proton will delocalize with this carbonyl carbon to give you a enol form, which is reversible reaction, right? So if you have a alpha proton which is present in the system, then it can show you the keto-enol tautomerism. Okay. So now coming back to the question. So now just quickly tell me which is the compound which is not going to show you the keto-enol tautomerism.
Option B.
Second option.
Option number 2. Okay. Any other answer? Okay. So one by one we will go through it. So here this carbon and this is the carbonyl carbon, right? So here you will have hydrogens at this position, right? This position you will have the hydrogen and even you have this hydrogen as well, right? So there are possibility of this two hydrogens to give you the keto-enol tautomerism. But if you see in option number B, you have only this bridgehead proton and this position is blocked as you have two methyls which is present at the alpha position. So see, this is also the alpha position. And now if you locate the alpha protons for this option number C, then you can see that yes, here you have four alpha protons. Similarly for this is the alpha position. Again, this is the alpha position, this is the alpha position. So you are saying that option number B is the correct option, whereas you have this alpha proton which is present at this carbon. So it can also show you the keto-enol tautomerism. Why it is not showing? Can anyone tell me why?
Planarity.
Minority. Okay. So here, as we can say in option number A and B, there is a only difference in the presence of this alpha hydrogens, whereas in this case they have two methyl which is present, right? This is the same. This is the main difference between option number A and B. So guys, what will happen in option number B? Here, if you take this proton and go for the ketoenol tautomerism, then you will generate a double bond at this position, right? So this is the bridgehead carbon, this is the bridgehead carbon, and this is the bridgehead carbon. So the alkene, that is the double bond, is getting generated at the bridgehead position. So according to the Baldwin rule, so if you have come across the Baldwin rule, what is it he saying? That the double bond at the bridgehead positions is highly unstable. So it will not get generated at all. So if the compound has a preference, if a compound has an option to generate a double bond at the bridgehead position, then it will not prefer it. So bicyclic system does not prefer the generation of the alkene bond at the carbonyl carbon center. So that is why even you have this alpha proton at this position, here the ketoenol tautomerism is not going to show up because the double bond which is getting generated is highly unstable, and this will become a highly unstable molecule. So molecule will not prefer to go in that stage. Okay, so that is why in the case of B, it will not prefer to give you the ketoenol tautomerism unless you have this kind of proton at this position. You are not going to see the ketoenol tautomerism. So option number A is going to see you the ketoenol tautomerism. Option number C also going to give you the ketoenol tautomerism. D is also going to give you the ketoenol tautomerism having higher acidic alpha protons. But only B is the part at which you cannot see the ketoenol tautomerism, even though you have the alpha proton present at the center. So option number B will be the correct one. So is it clear why option number B is not going to see the not going to show the ketoenol tautomerism? So is it right, guys? Is it clear to all of you? Should I move forward? Anyone please respond.
Yes, ma'am.
Okay.
Yes, ma'am.
Then going to problem number 9. So we will be going fast now. So problem number 9. So they are asking you predict the major product of the following addition reaction using the Felkinan model. So you have to predict this major product using Felkinan model. So if you have this chiral alpha beta, chiral carbonyl compound, if you have this chiral center at the alpha position of this carbonyl compound, then a model is operative, that is the Felkinan model. So you have to add this nucleophile at this carbonyl carbon, and the stereochemistry is dictated by the Felkinan model. So according to that model, you have to answer the major product, right? So first of all, the nucleophile is getting attached. That is, the nucleophile is methyl here. So methyl lithium they have added. Methyl is the negative charge containing the nucleophile, and lithium is positive. So here the nucleophile is methyl, and methyl has to attack on this carbon. So first of all, we need to know what is Felkinan model. So Felkinan model is, first of all, you have to arrange your carbonyl groups and the small group, medium group, and large group which is present at the alpha center according to this Newman projection. So here there is a carbon which is the front carbon, that is the carbonyl group carbon, and the second carbon, that is the alpha position carbon. You have three substituent. This is hydrogen, that is the small substituent. This is the large substituent, and this is the medium substituent. Right? So hydrogen is the small substituent, pH is large, and methyl is medium. So you have to classify the alpha substituent first of all as small, medium, and large groups. Right? And after that, what you have to do? You have to draw this Newman projection in which carbonyl group carbon is upside. So here this carbonyl and R is hydrogen in our case. So this is hydrogen. So this is hydrogen. So now we have figured it out that yes, this is the pH group in our case. Medium is methyl group for our case, and small is the hydrogen group. Right, now you have to arrange these substituent like this. In the Newman projection, you have to draw it like this and you have to arrange it. Why? Because there is a concept behind it. See, if you rearrange this substituent, then you will see that yes, nucleophile is adding to this carbonyl carbon from a trajectory that is hindered. See, nucleophile has to attack on this carbonyl carbon, which is from that side, which is less hindered. So the trajectory is such that here this small group will arrive at the pathway. So the nucleophile will attack from this to this position, and the trajectory should be like that, where it will not see any large group in the trajectory. So there should be no hindrance when the nucleophile is adding on to carbonyl group. So here carbonyl carbon nucleophile is getting attacked from the side which is less hindered. So S group, that is the small group, is coming in the trajectory. So that is why this model is designed. So here large group is phenyl, R, that is hydrogen in our case, attached to the carbonyl carbon, and small group is hydrogen, and methyl is the medium group. Okay. Is this much clear to all of you? This much, this part.
Yes, ma'am.
Okay. Now nucleophile has to add, right? So nucleophile, if it is adding from here, opposites from the large group, then you will end up having this, because now the carbonyl double bond will reduce to OH. So here you will get this pH again. Just put your substituent at this position and you will get the answer very quickly. So this is the model which will ease your things. So this is the hydrogen. This is also the hydrogen, right? Right. And nucleophile is methyl. Methyl lithium is getting attached, right? So we have methyl as a nucleophile. So now if it is getting attached here, then you have all the things at place. Now you have to answer according to this stereochemistry, that is wedge dash model. So you have to draw this wedge dash model. You have already arrived at particular configuration and now you have to draw the wedge dash. For that, what you need to know is methyl and phenyl are anti to each other. So you have to draw the Newman projection where phenyl and methyl are anti to each other. And then you have to arrange the hydroxy and methyl. So here, if Newman projection has to be drawn where OH, where phenyl and methyl has to be anti. So you have to rotate the things. So phenyl of this and methyl of this should be anti to each other, right? So if you can see from this side, this is also already anti, but I am drawing it. So if I am placing pH at here, methyl at here, right? Then what will happen? If pH is coming here, then what is this position? Here, what should be added? Can anyone tell me? What should be at this position?
H hydrogen.
H, right? H would be at this position. And here you will have this methyl, right? So now coming to this position, what should be at this position? What should be at this position, guys? It should be hydrogen and it should be hydroxy. Just draw it and you will understand it. Just move the bonds according to the thing that phenyl and methyl should be empty, because in the option the phenyl and methyl are empty. That is why we are just taking this reference and drawing it like this. Okay, and you know that, and you know already how to draw the Newman projection, how to draw the soy horse, how to draw the Fisher projection. So here only you need to know it, you need to do is the rotate the bonds. Rotate the bonds such that phenyl and methyl should be empty. Then you will arrive to at this particular configuration for sure. Okay. So now you can see here that both this hydroxy and methyl is coming at one position, and this hydrogen and hydrogen is coming at similar position. So in the case of option 1, hydroxy and methyls are anti to each other and hydroxy and methyl are syn to each other. Then option C is stating that both the products are in 1:1 ratio, and fourth is stating none of the above. So you have to figure it out the major product. So I'm not saying that minor product is not there, but the question is asking you the major product only. So major product is the product where the nucleophile trajectory is less hindered. So small group will arrive at the trajectory of nucleophile. So now just tell me which would be the possible answer for the major product. Stating that
Option number B.
option number B, because hydroxy and methyl are coming at one position and hydrogen is coming at one position. So hydroxy and methyl should be syn to each other and hydrogens are syn to each other. So here in option number A, OH and methyl stereochemistry is anti to each other, which is not possible in our case, right? The thing which we are arriving at. But in option number B, hydroxyl and methyl are syn to each other, and hydrogens are also syn to each other. Either way, you can write it both anti, both alpha, both beta, you can write, but you have to just arrive at the stereochemistry. You just need to see the stereochemistry of OH and methyl. They should be same. So in option number A it is different, option number B it is same. So option number B is the correct one, because both the product could not be formed in 1:1 ratio, because one has to be major and one has to be minor, and none of the above is not the case. Okay, so option number B will be the right option for this problem. You can see here also the nucleophile has to add air, and you just have to the largest substituent in its own plane and this smallest substituent in the Burgee-Donitz trajectory. The trajectory which is followed by this nucleophile is known as Burgee-Donitz trajectory. So that is why it should be facing a small group while coming to the carbonyl carbon, and here this is the major stabilized product. That is why we are saying that the yes, the major product would be that. Is it clear to all of you why option number B is the correct option?
Yes, ma'am.
Okay. Coming to similar question like this. Problem number 10. In the following nucleophilic addition reaction, you have to identify the major product. So similarly, you have to answer for this as well. Similar question is there. So here you have this hydrogen, methyl and OSIPH2. So this is also chiral. Now you have to add this group. Instead of this methyl group, you have to add this particular allyl group at this position. And TBAF is the, it will deprotect this allyl to get you the OH. This is the deprotecting agent only. So this will, TBAF will deprotect this allyl group and this will generate a OH. So that is why you in the final product you are getting this OH. Okay. So similarly you have to draw this for this as well. So if it is better to draw in that particular thing only. Okay. Coming to medium, small, and large group. So large group is this OSIPH2. So I'm placing it here. OSIPH2. See, I'm just writing OSI. Then hydrogen and methyl. So hydrogen will be this, methyl will be this. And from the carbonyl carbon point of view, this R is methyl. Nucleophile is this allyl group. Nucleophile is this allyl group. Right? So this much you have already done. I'm just placing the substituent, okay? Just practice it and then you will get it. Now nucleophile is this allyl group. So instead of methyl, you will have this allyl group which is add to it. OH is there after the deprotection. Phenyl is OS after the deprotection. So here OH is there at the large group because OSI is getting deprotected by DBAF. Okay. Now this is methyl. This H group is small group is hydrogen only. M group is methyl only. Okay. So now you have to draw. Now you have to draw with anti this and anti methyl. Right. If you draw it with anti this and methyl group at anti, just tell me the substituent. I have told you previously. Now you have to tell me what will be the substituent which will arrive here if methyl has to go. This is the methyl of this. So this is the large group basically. So you have to rotate this methyl. So after rotating this methyl, what will happen? What will come at this side? OH, H. Then what will happen at this side? H, OH. Is it right, guys? Just see if you can, if you are able to get this. This is a nucleophile, okay? If I am talking about this, so if this is the nucleophile which is here, then this is attached to hydroxy and methyl, right? So one of this is methyl. Yeah. Yeah. So this is what you have arrived at. So now you have this OH and methyl at one position, and you have this OH and hydroxy at one position. So just remember this. One of the hydroxyl and methyl should be syn, and one hydroxy and one hydrogen should be syn. So coming to option number A, one hydroxy and one hydrogen is syn, and one hydroxy and one methyl are syn. Now coming to option number B, this OH is syn to OH. Is it right? The OH is syn to OH. Is it right, guys? Should this OH should be syn to this? No, right? So here it will get eliminated, and this is getting eliminated because the this nucleophile is not at all adding to it. Only the deprotection by TBAF is going on. Only this OSI is deprotected, and this is as it is. So it is getting eliminated. So both A and B. We have seen that B cannot be formed because OH and OH, both the hydroxy, are not coming at the same position. So that is why B is getting eliminated, and the option number A should be the right answer, because as we have arrived at this structure, one hydroxy and one methyl should be syn. Here you have this one hydroxy and one methyl, which is syn, and one hydroxy, one hydrogen, that is syn. So is it right? Is it understood? Is it understood, all of you? Or should I have to repeat it? Is it clear, guys?
Yes, ma'am.
Okay, then if it is clear, then moving very fast to problem number 11. So now, see, please practice the Spelkin and model questions, because they are stereochemistry based question, and they are very simple to understand if you understand the logic behind it. Okay, just know the stereochemistry, know how to draw the Newman projection, how to rotate the things, how to see the things. You will get the answer very quickly. So in problem number 11, they are asking which ester will not give you the good yield for Claisen condensation product with sodium ethoxide ethanol. Now you need to know what is Claisen condensation. So this is Claisen condensation. Alpha hydrogen is abstracted by the base, and then enolate is getting generated. So basically enolate is getting generated. So higher is the stability of enolate, higher will be the rate of the Claisen condensation. So this Claisen condensation will go forward once this reversible step is stabilized. Higher the generation of the stable enolate, higher will be the rate for the Claisen condensation. So similarly, now you have to apply this concept to this particular options. So now just tell me which compound will form the least stable enolate. Which will form the least stable enolate, guys? Enolate means alpha proton is getting abstracted and carbon ion is getting generated. Now tell me which is the least stable carbon ion.
B.
Tell me, is it is the easy thing now. Tell me which is least stable carbon ion.
C. C option.
C. Very nice. Because it is having two methyl group which is attached to it, and the electron crowding is there. That is why this negative charge is less stabilized, least stabilized, because the R group is 1. At this case, R group is 2, R group is 3. Here the Cl is present, that is electron withdrawing group, which is stabilizing somehow stabilizing this negative charge. But the least stabilization is there at this option number C, and that is why the enolate is what? This carbon ion is resonate with this particular carbonyl group. So enolate that is generating at the C option is least stable. That is why it is not going to give you a good yield for Claisen condensation, because for Claisen condensation the main thing is higher stability of the enolate that is generated. So here you will get the less yield for the Claisen condensation. So option number C is the right answer. So is it clear? Okay, if it is clear, then I'm moving to problem number 12. So it is a very simple question, aldol condensation only. So you have to answer which combination of carbonyl compounds will give you phenyl vinyl ketone, which is this phenyl vinyl ketone, by the aldol condensation. All of you know the aldol condensation mechanism. Now tell me what will be the combination between these two four will give you the phenyl vinyl ketone on aldol condensation. Is it the acetophenone ketone, acetophenone aldehyde, benzaldehyde aldehyde, and benzaldehyde ketone? Any answers? So first of all, need to know the aldol condensation. If you don't know what happened in the aldol condensation, alpha proton is getting abstracted, and then it will attack in this. Particularly it is attacking on the second molecule of this only, but here you have a choice that acetophenone and ketone is going to react. If this is the acetophenone moiety, see, now if it is attacked on this is also R and this is also R. If this is ketone, then what will happen? This negative charge will goes to this carbonyl carbon, and this is how you will get this beta hydroxycarbonyl, right? So in our case, what will happen? This beta hydroxycarbon, if it is attacking from this side or this, doesn't matter if it is attacking to this. In our case, in this case, they are attacking this carbonyl group and it is going to alcohol. So here you are getting this beta hydroxycarbonyl. So instead of this, we have phenyl group attached to the carbonyl, as I have told you, phenyl group attached to the carbonyl with this. So if this aldehyde has to be attacked and ketone has to be attacked. So now you have to answer according to the attacking positions. Just think, if you have this ketone and if you have this aldehyde with you, this is aldehyde. So carbon ion getting generated here, and you are getting two options to attack this or to attack this. Now what will happen? You are having this carbonyl group at this position. This is hydrogen. This is the OH group with this. In our case, it is methyl. It is methyl. It is, see, if the ketone is going to attack, ketone is going to attack means you have this methyl here and methyl here instead of R positions, right? And you have one methyl here and hydrogen. So if this carbon ion is getting generated and this is attacked by this, then you have hydrogen in the case of aldehyde and methyl in the case of ketone present here, right? So now one dehydration step will take place. So here OH and hydrogen will liberate to give you alpha beta unsaturated ketone, alpha beta unsaturated ketone. So this will get generated here. So in our case, we have hydrogens present at this position, right? So this combination will be having, if you have this acetophenone and ketone with this. So if you give the aldol condensation of acetophenone and ketone, then you will arrive at the phenyl vinyl ketone. As the name suggests, you will first do the aldol condensation, abstract the alpha hydrogen, attack to the respective aldehyde ketone, and then you will do the dehydration step to yield to get the alkene generated to get this phenyl vinyl ketone. So here, after doing the aldol condensation of acetophenone and ketone, you will arrive at this moiety. So option number A will be the correct option for this. You will arrive at this moiety after reacting acetophenone and ketone. Okay, is it clear? So just do the aldol condensation. See, first of all, you need to know what is aldol condensation. Just write down on it on the paper, because the topic for today is such that you have to write it. If you try to think over it, then you will not get it. Just write on the piece of paper and then you will realize, yes, the bonds is migrating like this only. Okay. So coming to problem number 30. So this is again a very simple problem, guys. So in the compound there are three carbon oxygen bonds and they are telling you to decide the length. So this is X, Y and Z. Now you have to arrange it according to their lengths. So quickly tell me what should be the correct answer. If X is the length of this carbonyl group, Y is this CO and Z is OCH3. What should be the trend for their lengths?
Option 3.
Option 3. Okay. Any other answer than this? Okay. So before answering it, you first need to know that this oxygen is also participating in the delocalization, right? So if it is participating in the delocalization, then there is a partial positive charge which is also getting at this Y position. So now your length for this X and for this Y will become equal because now there is a resonance which is occurring between this carbonyl group, right? So X and Y length should be same because there is a constant resonance. But if you talk about this OCH3 bond, then it should be a single bond. So just tell me the double bond is smaller than the single bond. So the same concept lies here. If you are arriving at a partial double bond character at this position and this position, then X and Y bond should be smaller than OCH3 bond, that is the Z bond. Because now you have a single bond, that is Z bond, and a partial double bond character is arising between X and Y. So X and Y bond is equal to each other, but Z bond is larger than X and Y because single bonds are the length of the single bond is smaller than length of the double bond is smaller than the single bond. So that is why you can say because of the resonance X is equal to Y but is less than Z. So now tell me which is the correct answer?
Option 2.
Option B.
Option 2. So is it understood, guys, why X is equal to Y but less than Z? Is it clear? Is it
Yes, ma'am.
okay? So if it is clear, then coming to problem number 14, quickly just answer it. What is this? Now they are asking you what is the major organic product obtained from the following reaction. What is the reaction? Ketone is there, amine is there, primary amine is there, and you have to do the hydrolysis as well. So now tell me which would be the correct answer, which is the correct option. It's a very simple question.
Option C.
Option C. Any other answer than option number C? Okay.
Option B.
Option B. Okay. So guys, what will happen? First of all, this is a primary amine. It will attack to this carbonyl compound. It is a basic species. Now it is a electrophilic center. Now this O minus will get generate, right? Just go through this mechanism. First of all, in the acidic medium, this will get protonated, the carbonyl oxygen, and then this primary amine. In our case, we have a primary amine. They are describing about the secondary amine. So we have this again one hydrogen which is present and this methyl. Now this amine will attack on the carbonyl carbon and will leads to formation of this OH. So now N will get a positive charge with another hydrogen present here and one methyl group which is present here, right? So now what will happen? It will one proton it will take up and neutralize the charge. So this much you will get it. But now they are again hydrolyzing it, right? They are again hydrolyzing it. So now you have another hydrogen which is present with this nitrogen. in our case, because we have a primary amine species. So instead of going from the ring, now it will prefer to knock out this OH2 molecule, which is forming by the hydrolysis by its own, because in the secondary amine case there is no option for the amine to liberate the OH2 by its own. That is why a enamine is forming. In the secondary amine case, enamine formation is taking place, but in the primary amine, what will happen? This nitrogen is already having lone pair and presence of this hydrogen. So here, this hydrogen will go here and this OH2 will leaves out to give you a moiety like this. So here you will have this double bond nitrogen and CH3 from this. So is it understandable? Is it clear to all of you why enamine is not getting generated, but this molecule is getting generated because of the presence of primary amine in the system? Is it clear? Is the mechanism clear to all of you?
Yes, ma'am.
Okay. Tell me the answer then. Which is the correct option?
D.
Option number D.
D.
Option number D will be the correct one. If you have the secondary amine, then enamine formation will take place, because now nitrogen doesn't have the possibility of liberation of any of the hydrogen to hydrolyze and to get the double bond at the exocyclic position. So coming to problem number 15. So this will be the last problem for today. So this is also a very simple problem based on the mechanism only. So now they are asking you what is the major organic product obtained from the following reaction. So they are treating this ester group with diabyl H, and second step is hydrolysis. So what is diabyl H? Can anyone tell me what is diabyl H? Oxidizing agent, reducing agent, what?
Reducing agent.
Yeah,
Oxidizing agent.
not oxidizing, it is the reducing agent. Why?
Reducing.
Because diabyl is the diisopropyl aluminum hydride. So here you have, similar to lithium aluminum hydride, diabyl is also there, but what happens in diabyl, you have this isopropyl group which is attached. So here you will get a selectivity. It is only having one hydride source. It is a single hydride source. Whereas in the case of lithium aluminum hydride, there are four hydride which is available. But in the case of diabyl H, there is only one hydride that is available for the reduction of the carbonyl group. So similarly, as I have explained in the lithium aluminum hydride, hydride will transfer to this carbonyl carbon, oxygen then chelate with this aluminium. Similarly, here also this hydride will come here at the carbonyl carbon. This will chelate to give you this tetrahedral intermediate, and after that, what will happen? They have hydrolyzed it, and I have told you after the hydrolysis, this O aluminium bond, oxygen aluminium bond is broken down, and you will get the OH formation. So after the formation of OH or O minus at this position, what will happen? You have a leaving group, guys. You have a leaving group present, OCH3. So after it come down, then this OHCH3 will leave out to give you this ketone. So if you are starting with this ester, you will end up having the aldehyde in the hand rather than the alcohol. So what is the advantage of using diabyl H? It will give you a single reduction product, not giving you the alcohol. If you use, instead of this diabyl H, if you use here the lithium aluminum hydride, then you have 4 hydride which is present, right? So as soon as you have generated a ketone, then again one another hydride of this lithium aluminum hydride will give you this attack and you will get generated a alcohol. So the advantage of using diol is it is giving you the selectivity. So selectivity is given by diol, as you can selectively reduce ester to aldehyde, but lithium aluminum hydride is very strong enough to give you ester, to give you from ester the alcohol. So direct reduction will take place, but in this case you will end up having this ketone in hand rather than the alcohol, because it is a single hydride donor. Okay. So now tell me, what will be the possible product in this reaction?
C.
C.
A.
C or A. This is ester and hydride has to add. We are not going to hydrolyze this ester. See, here if the hydride is adding, then after coming down, OH is a good leaving group or OCH3 is a good leaving group. Of course, OCH3 methoxy is a good leaving group, right? So that is why it is going to leave, and then aldehyde is getting generated. So here also you will generate a aldehyde. So aldehyde is getting generated at this position. Ester is going to aldehyde. This part is not going to be touched, but this ester is reduced to aldehyde. So option number C will be the correct option. So is this much clear to all of you?
Yes, ma'am.
Okay. So I'm closing this session now. So I hope all of you have understand the topic. And if it is not clear to any of you, please try to contact me in the second lecture I will be taking. Then you can ask me the question which you have, or in the comment box of my YouTube channel you can ask there also. But it's better to ask in the next lecture, so that everyone will know your query and everyone will know the answer. Okay. So thank you so much for joining the session. I'm just shutting the lecture down. So thank you so much for joining.
Thank you, ma'am.
Okay. Thank you.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you.